Okay, so for this final example of splitting, we're just going to go back to the original example of ethanol that we used for low resolution. And you remember we had this integration situation whereby we had the one proton on the left due to the OH, CH2 in the middle, and the CH3 on the end. Remember, this was low resolution. However, now what we're going to do is we're going to make this a high resolution spec by introducing splitting and make it a little bit more realistic about what we'll actually see. So we need to look at each individual peak in turn. And so what we're going to do is we're going to look initially, we'll go from right to left. So we're going to look at the CH3 peak on the right hand side. Remember, the area under that curve is 3 due to the CH3. However, that is going to be split now, as we know, by the protons on the adjacent carbon. So there are 2 hydrogens on that adjacent carbon. And so we are going to see, remember, n+1 rule. So we are going to see the presence of 3 peaks, a triplet. And a triplet has an integration ratio of 1 to 1 when we see the presence of that triplet. So this peak on the right hand side is going to be split into a triplet with 1, 2, 1 heights. Okay, remember the integration under that curve is 3 due to the presence of the CH3. The triplet is due to the adjacent presence of a CH2. Okay, so now what we'll do is we'll look at the middle peak, which is a CH2 peak. That is adjacent to 3 hydrogens. It is not adjacent to the OH hydrogen. Splitting only occurs when you have hydrogens attached and adjacent to carbons. The presence of the oxygen stops the splitting going through to that adjacent hydrogen. The hydrogen on the OH is adjacent to the CH2, however, it doesn't contribute to splitting. We only see splitting when we have adjacency on carbons. So that CH2 then is split by 3 protons. So n+1 gives us 4 peaks. And remember, the integration ratio of those 4 peaks will be 1, 3, 3, 1. So 1, 3, 3, 1 as an integration ratio. Remember, the area under that curve would be 2. The area under the first triplet would be 3. And as we just said, because we don't get any splitting through oxygen or via oxygen, we don't see any splitting of this final proton of the OH. We don't see that hydrogen split by the adjacent CH2, so that remains as a singlet. Okay, and that would be the name given to that. So we would have a singlet here with an integration of 1. We'd have a quartet here with an integration of 2. We'd have a triplet here with an integration of 3. The position, obviously, with the ppm scale, you'd use the table on the back of the periodic table. The triplet would be somewhere in the region of 1 ppm, give or take, obviously. The quartet would be slightly more downfield due to the presence of the electronegative oxygen. This might be something in the region of 2 to 3 ppm, and then obviously the singlet might be somewhere in the region of 6 ppm. As I say, you don't need to memorize these numbers, just using these as examples. In a few more clips, we'll look at some specific examples with real numbers and real data, but this hopefully giving you a general overview of what we can do.